Good morning, guys. Myself, Shridhar, working as the assistant professor in Electronics and Communication Department of Government Engineering College, Haveri. So today, just we are dealing with the basic electronics subject in that module 1, semiconductor diodes and application. In that, the session 5, that is bridge rectifier. In the previous session, we just discussed about the half wave rectifier as well as bridge. So in the previous session we just discussed about the bridge half wave rectifier as well as full wave rectifier. In the full wave rectifier we discussed about the center tapped rectifier. So in this session we are just going for the bridge rectifier. Okay, so where we are using 4 diodes for the connections. Okay, bridge rectifier. The bridge rectifier circuit is made up of 4 diodes D1, D2, D3 and D4 and a load resistor RL. The 4 diodes are connected in a closed loop configuration to efficiently convert the alternating current AC into DC. The main advantage of the configuration is the absence of the expensive center tap transformer. Therefore, the size and cost are reduced. So, this is the thing. So, we are concentrating on what? Here the center tap transformer is not been used, and we are using 4 diodes D1, D2, D3 and D4, and sometimes we will be telling it as D1 and D2, D3 and D4. See the directions D1 and D3. In this figure we have to mention it as D1 and D3 are in a same direction and D2 and D4 are in a same direction, and it is left to you. So you can represent anything. D1 and D2, D3 and D4 also can be represented. Okay, here the input signal is applied across the two terminals A and B, and the output DC signal across the load resistor RL connected between the terminals C and D. A and B are the what? The two terminals, and the diodes are being connected, and the load resistors is being connected across the terminals C and B, and the output current is being considered across the load resistor. The 4 diodes are arranged in such a way that only 2 diodes conduct electricity during each half cycle, D1 and D3. Only during the positive half cycle D1 and D3 will be conducting, and in the negative half cycle D2 and D4 will be conducting. At the remaining state it will be off. Likewise, the diodes D and D2 conduct electrical current during a negative half cycle. Next we will just going for your working of a bridge rectifier. See here, if you just go through the circuit, see here, the diode during the positive half cycle, the two diodes D1 and D3 are forward bias, that is it is in a closed switch. So there is a flow of current across the load resistor RL, and the diodes D2 and D4 are in a off state. So these are in a off state, means the diode D2 and D4 are in a reverse bias, and there will be no flow of current. Okay, see here. So this results in D1 and D3 to become forward bias, and D2 and D4 become reverse bias. So next, in the negative half cycle, what is happening? Same thing. D1 and D3 are in a reverse bias, D2 and D4 are in a forward biased, and the load the output is current is being considered across the load resistance RL. Okay, see, this is the input and output. During the positive half cycle, what? D1 and D3 are been conducting, and during the negative half cycle D2 and D4 are conducting. That is, during the positive half cycle D1 and D2 are in a forward bias, and in the negative half cycle D2 and D4 are in a forward biased. So this is the waveform what we will be getting. So it is same like as your center tapped full wave rectifier. Only thing is the efficiency will be just equal. Okay, the output is proportional to be either completely positive or negative. In our case, it is completely positive. If the direction of the diode is reversed, then we get a complete negative DC voltage. The bridge rectifier allows electric current during both the positive and negative half cycle of the input AC signal. So these are some of the characteristics. So first is the ripple factor. The ripple factor is defined as the ratio of the ripple voltage to the pure DC voltage. In the formula for the ripple factor, it is same as with the full wave rectifier, that is a center tapped full wave rectifier, that is gamma is equal to square root of Vrms by Vdc whole square minus 1, and the ripple factor will be always 0.48 and efficiency, and it is also same as the center tap, and the efficiency is being given by the 81.2, that is DC output by AC output. Next, the PIV, that is the peak inverse voltage, the maximum voltage that the diode can withstand in the reverse bias condition is known as the peak inverse voltage. During the positive cycle, diodes D1 and D3 are in the conducting state, while D2 and D4 are in the non conducting. Same thing what it has been explained previously. Next, so these are some of the advantages as well as disadvantages of a bridge wave rectifier. So what are the advantages? Means here we don't require center tap transformer. Okay, that is the need of center tap transformer is eliminated, hence the cost is reduced. Since we are not using the center tap transformer, the cost will be obviously reduced, and only the 4 diodes will be just arranged. The output is twice that of the center tap circuit for the same secondary voltage. See here, the output is also been twice, that is been efficiency is also been increased. The peak inverse voltage is one half that of the center tap circuit of the same DC input. The disadvantage is, though we are not using here the center tap, but we require here 4 diodes. 2 diodes in series conduct during each half of the AC. It increases the total voltage drop and losses. Okay, so now the applications of bridge rectifier, where this bridge rectifier has been applied. So full wave rectifier finds use in construction of constant DC voltage power supplies, especially in general power supplies. The full wave rectifiers are used in the power supplies. A bridge rectifier with efficient filter is ideal for any type of general power supply applications like charging a battery, powering a device like motor, LED, etc. Okay, so in any of the power supplies, so your charger batteries also will be using your bridge rectifier. Okay, so this one is the comparisons between the what we have studied, half wave rectifier, full wave rectifier, as well as your bridge rectifier. So these are some of the parameters. The first, the DC or average load current ILDC is equal to what? For half wave rectifier it will be 2 Im by pi. For full wave rectifier as well as for bridge rectifier it is 2 Im by 5. Okay, you should be remembering all this just for the calculation purpose. The maximum average load voltage VL is given by Vm by pi, and it is twice compared to half wave rectifier, so it will be 2 Vm by pi for both full wave rectifier as well as the bridge rectifier. And the RMS load current IL, that is Im by 2. So here it is for full wave rectifier as well as for bridge rectifier it is Im by root 2, and the RMS load voltage IVL LMS is equal to Vm by 2 for half wave rectifier. The same for full wave rectifier it is Vm by root 2, as well as for bridge rectifier it is also Vm by root 2. The DC load power is given by PDC. For half wave rectifier it is I square M by pi square into RL, and it is twice for full wave rectifier, that is 4 I square M into RL by pi square. And for bridge rectifier it is also same. And the rectification efficiency for half a rectifier is 40, and for full wave rectifier as well as for bridge rectifier it is 81.2, and the TUF will be 28.7% for half a rectifier, and for full wave rectifier it is 69.3, and for bridge rectifier it is 81.2. The ripple factor for half wave rectifier it is 100%, but for full wave rectifier as well as bridge rectifier it is 48%, and the ripple frequency for half wave rectifier it is 50 Hz, and for full wave rectifier as well as for bridge rectifier it is 100 Hz. The number of diodes for half wave rectifier we require only 1 diode, for full wave rectifier we require 2 diodes, and for bridge rectifier require 4 diodes. And the center tap transformer for we don't require for half wave rectifier as well as bridge rectifier, we require only for full wave rectifier. Transformer core saturation it is possible, and for in half wave rectifier, but in full wave rectifier as well as bridge rectifier it is not possible. And the PIV, peak inverse voltage, is given by Vm in half wave rectifier, 2 Vm in full wave rectifier, as well as for bridge rectifier it is Vm. Expression of the peak load current PIL is being given by IM is equal to VM into RS plus RF plus RL. IM is equal to VM RS plus RF by RL. So it is same for all the three, but only for bridge rectifier it is VM is into RS plus 2RF plus RL in the circuit diagram. Okay, only for half rectifier one diode is used across and the load resistor. For full wave rectifier along with the center tap transformer, we require two diodes along the load resistor, and for bridge rectifier we don't require center tap but transformer, but we require four diodes with the load resistor RL. Okay, see the comparison between the same half wave rectifier as well as bridge rectifier. So the schematic diagram of a half wave rectifier, full wave rectifier as well as the bridge rectifier. So this one is the typical means during a positive cycle only the output current is being formed, but in full wave rectifier the spikes for both positive as well as negative spikes have been getting, for in the same pattern for bridge rectifier also we are getting the same. Okay, so what we should be requiring maximum in this half wave rectifier, full wave rectifier and center bridge rectifier is number of diodes, that is for half wave it is 1, for full wave it is 2, that is center tap, and for bridge type it is 4. Transformer necessary, for how is it transformer necessary for half wave rectifier? No. For bridge rectifier also it is no, but for center tap it is yes. The maximum efficiency for half wave is 40.6%, and for full wave as well as for bridge rectifier it is 81.2, and the ripple factor it is 1.21 for half wave rectifier and 0.48 and 0.48 for center tap full wave rectifier as well as for bridge rectifier. Output frequency is Fin for half wave rectifier to Fin for both center tap as well as bridge type. Peak inverse voltage it is Vm for half wave rectifier as well as bridge type, but for center tap it is 2 Vm, that is V1 plus V2. Okay, so we're just going for this problem. Okay, for a bridge rectifier. So depending upon the previous characteristics, the first thing is the given problem statement is calculate the VDC average for a 4 diode full wave rectifier that is connected to the secondary of transformer that provides 120 volts as 120 volts AC RMS, that is alternate getting RMS, that is root mean scheme. Remember to include that 1:2 voltage drop through the diodes. We know that equation Vp is equal to V sec RMS into 1.4, so minus 1.4 volts. So this one is the voltage drop, so we are just subtracting that value. See here, we are just subtracting this value, so we will be getting the Vp value after calculation is 168.28 volts, and we know that the VDC formula is 2 Vp by pi, so we will calculate, we will be getting it as 106.95 volts. Okay, see next formula. The next problem, in the bridge type circuit shown, the diodes are assumed to be ideal. Find DC output voltage, peak inverse voltage, output frequency. Assume primary to secondary terms to be 4. So this one is the problem what they are given, 230 volts, 50 volts. So Vm is equal to 230 and omega is equal to 50 volts, and the load resistor RL is equal to 12, and the turn ratio is given it as 4:1. Okay, so depending upon this figure, the values, the given values are what? Primary second terms is N1 by N2 is equal to 4. That is the secondary terms to be is 4. So they have mentioned it as N1 by N2 is equal to 4. The RMS primary voltage is 230 volts. That is Vm is equal to what? 230 volts. RMS secondary voltage. So primary voltage they have given calculated directly for 230 volts, and for secondary voltage how to calculate by using the formula 230 into N2 by N1, that is 230 into 1 by 4. So we will be getting the secondary voltage as 57.5 volts. The maximum voltage across secondary is Vm is equal to root 2 into what? V2, that is RMS of the secondary voltage. Vm is equal to 57.5 into root 2, so we will be getting it as 81.3 volts. So average current. So first thing is average current IDC is equal to what? 2 Vm by pi into RL. So 2 is Vm is being calculated. So it is 2 into 81.3 divided by pi into load resistance RL is given. So we will be getting the value it as 0.26 amps, and the DC output voltage VDC is equal to IDC into RL. So we will be getting it as 52 volts. Next, the peak inverse voltage of a secondary voltage, that is PI is equal to VM, that is 81.3. So whatever the VM value will be calculating, PI will be the same. So PI is equal to VM, that is equal to 81.3. In a full wave rectification, there are two output pulses for each complete cycle of the input AC voltage. Therefore, the output frequency is twice that of the AC supply frequency, that is F0 is equal to 2 into Fin, that is 2 into 50 is equal to 100 hertz. Okay, so in this session we have just discussed about the bridge rectifier. So where we require 4 diodes, we have just compared the 3 rectifiers: half wave rectifier, full wave rectifier, as well as bridge rectifier, and we have just calculated the problems on bridge rectifier. So this completes your rectification, that is the session 5, that is the bridge